should be able. Excellent.
So you can see the screen,
Yes.
right?
Yeah.
Okay. My name is Jesus Garcia Ramirez, and I'm going to introduce you our paper, Multi-Source Transfer Learning for Deep Informal Learning. The co-authors of this work are Eduardo Morales and Hugo Yair Escalante, and our affiliation is the Instituto Nacional de Astrofísica Óptica y Electrónica, INAOE. Okay, this is the content of my presentation. I will start with an introduction. Then I will describe some about transfer learning. Then I will show you our proposed method, multi-source transfer learning for deep informal learning. Then I will show the experimental results. And finally, I will show the conclusions and future work. I'm going to start with the introduction. So deep learning have been showing impressive results in different tasks. Here you can see three of them. First, AlexNet that improved the top 1 and top 5 errors in ImageNet competition in 2012. Other is AlphaGo that learns to play the game of Go with a combination of deep neural networks, tree search, and reinforcement learning. This beat to the world champion of Go, Lee Sedol, in 4 of 5 matches. And finally, a deep network that combine reinforcement learning with deep learning to learn to play different Atari games. And we use this domain to test our proposed approach. Deep reinforcement learning is applicable when we have long action state space, such as Atari game. Here you can see a projection of TSNE algorithm of the game Space Invaders. DQN is the first algorithm that learned how to play different Atari games with the same architecture and hyperparameters, and also outperformed human level in 30 of 47 games. Nevertheless, deep reinforcement learning algorithms such as DeepQ network carry out the same limitation of deep learning. Two of the most important are the long training times, even with specialized hardware such as GPU or TPU, and the necessary instances to obtain an acceptable performance. Transfer learning offers an alternative to reduce the training time and in some cases to improve the results from training from scratch. In this work, we propose a method based on transfer learning that uses the convolutional kernels of two source or pre-trained models in order to train a new target task with less parameters in deep reinforcement learning domain. Now I will show you some of transfer learning. In the traditional scheme of transfer learning in convolutional layers or even in artificial neural networks, in a target task, the weights of the new model used to train this task are transferred from a source task that is a pre-trained model that has a good performance in the trained models. Here we use these pre-trained models to begin the training from in the target task instead of use random weights. In some cases, the final of the last layers are initialized with random weights, and these are used to train the new game. Now I will introduce you our method, multi-source transfer learning for deep reinforcement learning. During the evaluation of some pre-trained models, we observed that the feature maps in the hidden layers are like the two images that I show you here. Some of them produce outputs with a uniform background, like the left figure. Another produce feature maps with diverse values, such as the right figure. So to measure this, we use the entropy value. So the entropy of the uniform outputs will have lower entropy than the diversity value output, like the right figure. Here, the kernels with more information are more transferable than uniform one. Once this is because uniform outputs contains in some cases zeros, and because of the ReLU activation function, it's difficult to optimize them. So these types of wave are more transferable than the other ones. We use the entropies produced by the convolutional kernels as input of a regression model to predict the performance of the pertaining model in a new task. And next, I will show you our proposed method. First, as input, we have a target task sample. In this case, we use Atari games, and we have the frames of a game that we want to learn, and different pertaining models. Then we evaluate a sample of the target task in the pertaining models, and we extract the feature maps in each convolutional layer. Then we discretize these the features maps, and we find the entropy of each one. Then as features of the regression model, we use the entropies that we find and the action spaces of the source and target task in one hot encoding. We train the regression model, and then we evaluate with more pertaining models, and we select those that they predict maximum performance. In this case, we will use 2 source tasks or pertaining models. We also hypothesize that it's not necessary to transfer all the convolutional kernels to obtain an acceptable performance. So we select the convolutional kernels that produce feature maps with the highest entropy values, and we build a new architecture with less units. The last convolutional layer and fully connected layers are initialized with random weights. And finally, we fine-tune the entire model. Here I show the architecture that we used. First, we select the convolutional kernel from each source, and we put it in a different model from source 1 and source 2. We transfer from each convolutional layer. Then we join the third convolutional layer, and we add an extra convolutional layer to learn a new representation based on the 2 representations that has been transferred. Finally, we add a fully connected layer and the output one. The weights that we transfer that I show here are freezed in order to reduce the training time. Now I will show the experimental results of our proposed method. In our experiments, we use the QN algorithm with dopamine RL library, and we train agents in 3 Atari games. These games outperform human scores according to the DQN paper. We select 2 source tasks with the best predicted performance using the regression that we trained in previous stages, and a half of kernels in each convolutional layer are transferred from each source. And we run in 3 independent experiments in each game in order to show the variation to initialize the last layers with random weights. To train the regressor, we select 12 of these 30 games, and we transfer the pertaining models between all of them. For the transfer, we transfer only the convolutional layers, and the last fully connected layers are initialized with random weights. We train a regressor with this training set, and the best hyperparameters are a random forest target with a random forest with 47 trees and mean square error as a quality measure. The scores that we use to rank the hyperparameters are the ranking in the first, second, and third position, and the lowest error. To build a new architecture, we follow the next steps. First, we rank the convolutional kernels according to the entropy values of the feature maps. Then we select and we sort them according to their entropy values. We select a half of kernel with the highest entropy on the pertained models, and we transfer those to the new architecture. The last convolutional layer uh, and the field connected layers are initialized with random weights, and according to the number of units that we select, our architecture has near 57% of parameters compared with the source model. We do the same process for the source number 2. Here's the details of the architecture. The transferred kernels in the convolutional layers. Here we have 3 convolutional layers. In the first convolutional layer, we transfer 16 filters. In the second convolutional layer, 32 filters, and the same number of filters in the third convolutional layer. Then the new convolutional layer that we add has 48 filters, and the fully connected layer has 384 units, and also the output layer, that is the number of actions available for the agent. Also, we do a hyperparameter tuning because of the instability of the learning curves, and the best configuration is to increase the batch size from 32 to 64 and reduce the learning rate. This obtains the avert area under the curve, and we select this configuration to train the new agents. According to the results that we obtain, we have 3 groups of results: positive transfer, neutral transfer, and negative transfer. In positive transfer, the agent outperforms the training from scratch, and here we obtain 20 of the 30 games this positive transfer. In neutral transfer, the mean of the 3 experiment is between the minimum and the maximum of the training from scratch, and we obtain this performance in 4 of 30 games. Finally, negative transfer, that the training from scratch is better than the multi-source transfer. We obtain this negative transfer in 6 of 30 games. Considering in general the experiments and the results in general, and we can show the next results. First, considering the best out of 3 experiments per game, we have a mean gain of 5.8 hours in general for the 30 games. We obtain an improvement in the scores of 20.62% compared with the training from scratch. And also we obtain improvements in the metrics proposed by Taylor, that are the maximum score obtained scores, the transfer ratio, the final performance, and the jump start. Now I will show you the conclusions and future work. So in this work, we introduce a method for transferring from 2 sources to a new task in deep reinforcement learning algorithms, specifically in Atari games. We fine-tune the added layers, and the transferred ones are frozen. The performance of the evaluation metric shows that transfer from 2 sources is better than training from scratch. There exists an improvement of 20.62% according to the maximum obtained scores. And the number of parameters in the target architecture is considerably lower than the source one, is between 53 to 53 to 57%, depending on the game that we are training. For future work, we would like to apply the proposed method in other domains of such as classification, and we also try to improve the games that obtain negative transfer using a different configuration of the hardware parameters. We also want to acknowledge to Laboratorio Nacional de Supercómputo del Sureste de México and the Laboratorio Nacional de Supercómputo del Bajío to provide the resources to run our experiments. So that's it for me. Thank you for your attention, and our code is available in the GitHub repository that is given here. Thank you, everyone.